All right, so here we go. Let's talk about drift velocity. Now, this is kind of a cool concept. When you turn on the lights, okay, the electrons from the switch might take hours to get to where the light is, but the electrons right by the switch, right by the light, will start to flow instantly because the electromagnetic wave that goes through there travels close to the speed of light. I mean, there's some it slows down a little bit, but the actual electrons they're bouncing around inside this wire something fierce. Okay, and that causes internal resistance. Okay, and heats the thing up. So here's the electric field going this way. So which way do the electrons want to flow? They want to drift. They want to flow this way. But notice their path that they're taking is there takes them forever to get going. So they only travel. The electrons only travel about 1 millimeter per second. So that takes a long time for them to traverse the wire. But the electrons are throughout the entire wire. So it's kind of like if say you're sitting on remember the old bench seating in a stadium where they don't have the individual seats anymore, and let's say there's 20 a bench will hold 16 people comfortably, but there's 20 people smashed in there. Well, what happens when somebody at the one end of the bench comes along and sits down really hard, smooshes everybody over? Well, the person on the end of the bench falls off. That's what happened instantly. It doesn't take it move on, move on, move. No, they all fall off instantly. So that's what happens here. Okay, now resistance in the wire, there's a potential difference across a conductor. How much current flows? If there's how much current flows, well, the ratio between the voltage and the current is called the resistance, and current is equal to voltage over I. Okay, so and it's called an ohm. So let's look at the math of that real quick. This is Ohm's law. All right, this is Ohm's law, and Ohm's law is huge. Ohm's law is what this chapter is all about, really. And in fact, when things start moving, everything is about Ohm's law. So we got a resistor, resistance is equal to V over I. And if something is ohmic, if a material is ohmic or a current is ohmic, that means V is equal to IR. Now, this doesn't happen exactly every time because most things, this is like the ideal world. And let's take a look and see what does resistance look like. Okay, let's see what that resistance stuff. Here's resistance. All right, I always think of resistance. Here's a resistor. All right, each substance has its own resistivity, as you will see in a slide coming up in a minute. All right, but let's take a look. So let's increase the resistivity a little bit. So then R goes up. Okay, we increase. I always consider going through a resistor is like going through a cave. If it's a long cave, I don't want to go in there. My resistance to going through there is not as high. And if the opening area, if the cross sectional area of the cave is really really small, if I have to get down on my hands or if I have to belly crawl through that cave, and so that area is really small, my resistance goes way up going through there. Okay, but if I have a nice fat cave, a really tall cave that I can stand and walk through, or a tunnel I can stand and walk through, and it's not very long, and therefore my resistivity goes way down, then I don't have and the resistivity of it really small, then I don't have much compunction. I don't care if I go through it or not. My resistance is low. However, if you have a low resistance, the wire burns up. As you saw, things get hot. All right, and we'll take a look at the current here in a minute. Okay, so V equals IR. So what we have here, this is huge. And it's considered, so let's, is this ohmic? This situation. Let's say I've got V equals 11.7 volts, and I've got I is equal to 2.5 amps, and my resistance, which is in ohms, and it's very fun to write. I like writing that. The big omega, right? And let's say R is 5 ohms. Then when I plug this in, I've got 11.7. Is that equal to 2.5 times 5? No, because what's 2.5 times 5? Not 12 or something. This is a stupid answer. I shouldn't make these up. Yeah, that's 12.5. It shouldn't be that way. Let's say this is times 4. Then this would be 10. 10 volts. The potential here is 10, so it's 2.5 times 4. Sorry about that. I should have made it 4.3 too. Yeah, that would have made it a little better even. But you see, so this is no. Most of the stuff we're going to deal with is ohmic. Okay. All right, out here. That's enough for this one.